Okay, so this is my mousetrap car project presentation. This is the car moving.
Go.
One of the first things I did was find the mass of the car, and I did this by using the sensors. And considering that 9.8 newtons is 1 kilogram, I ended up finding that the mass of my car was like around 3.9 kilograms. Then I used my position versus time and velocity versus time graphs to find the maximum velocity, which would later help me find the kinetic energy. Uh, this is the graph, and using this graph on Logger Pro, I found that the maximum velocity is at 5.5 feet per second. Using the equation E kinetic is equal to 1/2 mv squared, I found that it was around 5.9. We can find the energy stored in the spring by using an equation similar to the y equals mx plus b equation. That would be F is equal to 29 newtons per meter times 0.06 pi minus 0.5, according to my graph. And I ended up finding that the energy stored in the spring was 0.46 joules. This is basically the area found under the equation of the graph. And in my case, it was the area under the triangle. Using this spring constant, I found that E elastic, according to the equation 1/2 kx squared, was 6.96. These are the force diagrams for both when my car is speeding up and when it's slowing down. When it's speeding up, we basically ignore the air resistance, and we know that the velocity is moving in the positive direction and the acceleration is moving in the positive direction as well. We also know that when the car is speeding up, the friction is going in the same direction that the car is moving, and it's actually not opposing it, which is what pushes it to make it go. Friction pushes it to make it go. So our force diagram would be a vector pointing up for normal force, a vector pointing down for work. Wait, sorry, I meant the vector pointing down is weight, and the friction is moving in positive direction, as we've already established. Slowing down, the car is still moving in a positive direction, but at a slower speed, and its acceleration is actually decreasing. So it's moving in the negative direction while velocity is still moving in the positive direction. This time friction is opposing the movement of the car, which is why the car is slowing down. Sometimes the direction of the friction vector is difficult to understand, but we can use second law to figure out why. Again, second law is the sum of forces is mass times acceleration. So clearly if acceleration is negative, then the sum of forces would be negative as well. And speeding up, we see that weight and normal don't change, but friction does, and whenever friction because it's going to be the same. It's going to be equal to mass times acceleration. Whenever it's moving in the positive direction, so will mass times acceleration. Therefore, acceleration will be positive, and it's the same relationship slowing down. So there's a direct relationship between the two. Alright, energy flow diagram. Okay, so wound up, the elastic is at its maximum, and because it's not moving, the velocity is 0. The system includes the mousetrap car, and the second stage is when its velocity is maximum at 5.5 feet per second. Not all energy makes it to the final stage, and we consider this E dissipated. Using blocks, we could easily say that E elastic, is 4 blocks minus E 2 blocks is equal to E kinetic, which would be 2 blocks. Okay, now taking into consideration that E is equal to E elastic minus E kinetic, we can find it by plugging in all the numbers we already have. Because we know the equations for E elastic and E kinetic, and we've found the results earlier on, we end up finding that the total energy dissipated is 1.06 joules. Okay, and finally I found the displacement by using Lagrange's integral fit and taking the area beneath the velocity versus time graph, and it gave me that it was approximately 25 feet. And that's my mousetrap race car project.